Welcome back. Today we got another little project here. It's a power module for a dynamometer. No one knows if it works or not. We're gonna check it if it works. Obviously give it a little bit of a clean because it's a bit dirty. And I already removed the cover, so we have no burnt components. That's good. Okay, let me get the side panels off and we'll look inside. If it's clean and no burnt components, we're gonna fire it up and test it with a kettle also. So what we're checking for, that's the reason why we take it completely apart, is just burnt components, because these sometimes have issues. These are high-speed fuses here. They look good. There's nothing burnt over here. Check the fuses here if they're good, but everything looks pretty good actually, so we should be fine. Let me take the top off and have a look inside. If there is any dust, we're going to remove the dust first, and once it's okay, we put the front panel back and then fire it up. So looks good inside as well. It's surprisingly clean. I'm surprised that it's so clean, but everything looks really well. So of course we need to check function, because the output triac could be shot, but or some relays could be burned or whatever. But from what I can see here, it all looks very promising. It's not the youngest anymore. These things are pretty old. This is tested 1985. 22nd of February 1985 it was tested, the functionality. So this is 35 years, and for that it's really clean. Either hasn't done a lot of work, or it was just living in a clean environment, because these things can be really dirty. Okay, we just do an insulation check to make sure we have no shorts. The reason why we thoroughly check is this because the customer reported a fault, but I think another fault has been found, so the dyno itself had a fault. Luckily we have all the drawings, so it makes life a lot easier. Without drawings it just takes you longer to figure out what goes where. Anyway, we're going to check insulation resistance, and if the insulation resistance is fine, and it doesn't draw excessive current in idle, we're going to hook it up to some test equipment and give it a quick check. Okay, we have power, and we're drawing 0.1 amp, which is the idle current. That's fine. So yeah, 0.1 amp with a really poor power factor. Okay, I need to find the kettle, and then we plug in the kettle. We've got the power supply here supplying a demand, and that's what we're trying now. Okay, hopefully we got all the safeties right now. That's a dyno safety, and this is our internal safeties here. So let's power it on and see what happens here. Come on, L1, 100 milliamps. This is not exactly what I want. I want a little bit more. I should see some current here, because really mounting 3 amps now. It's not drawing anything, so not even the kettle is lighting up. Don't know what's wrong. Can't see anything faulty here. No, even that resistor looks good, but I can't see the safety relay to click in. So that should have come on actually. Really kicks in. no demand. So either the demand is the wrong way around, or some safety is broken here. Let's check that again. Maybe something is wrong. Well, it's getting a bit trickier now, because I think I'm close to it, because if you look at this, lights off, how it looks like, and what they describe here, I got the feeling that either this transistor or this diode is short, because I should see at least about 0.7 positive, because this is actually the rectified output of that transformer, and I can see the 100 Hertz on the other side, but this is so flattened, it just doesn't look right to me. So we'll check what's going on here with this diode and this transistor. Makes sense, because this is coming in here. If there was a high voltage or a spike or something coming out, it probably shot either the transistor or the diode, because there's something coming out here, but it doesn't look nice. These spikes, unfortunately, they don't tell you any levels here, but it's there, but not really, so who knows. Let's check these two. Probably something shot there. I got it a little bit better on the screen here, but yeah, the resolution on the scan is so poor. Luckily I found a paper copy, so it's in this area. We should see 0.7 volt positive, because that's 0 volts and that's a diode, so we should see 0.7 at the trigger point, which switches that transistor. I can see something on this side, but I just don't like how it looks like. It's so flattened, and it's I don't know, it's going too far negative as well. Well, yeah, it's negative voltage here. You can't really tell. Well, let's check the components, because the firing transformers are working here, so they are all good, and I can see this here, so that's all good. The pulse forming is working, but I don't know if anything comes out here. This is actually the pulse former, which, yeah, triggers the bottom end, so who knows. Let's see what we find. Don't know if it's visible here. Let's look at this one. It's probably better to see. I'm pretty sure our problem lies here, because this pulse level is on 14 volts. It's a sharp pulse towards 0, but it's never gonna go low. If you look at that, I don't know if it's visible. This is almost nothing. There's a bit of glare, but I don't know if it's visible. We're about here, which is 15 volts, and this is 17-ish volts. No, sorry, that's 10. That's 10 volts, and that's 14 volts. So we are hogging on our plus 14, which comes from up here. So this transistor doesn't pull it down. So we have a problem here. So I'm pretty sure if you measure here, there's nothing happening, or not much. All we see is the trigger pulse from the other side. Because this is plus 14, and that goes into the transformer in series down here. So we want to see something negative, but it doesn't go that far. That is probably our problem. And we get the pulses in here, which don't look very nice, but we get them. And if I measure here, we get them as well. So at TP5 we see that, which is about right. Well, let's try that again. Let's try TP5 again. The shape looks a bit different. So this is high current demand, and this is low current demand, which is about what we can see here on the diagram. But down here, these pulses, I expect something better. So we'll check what's happening at this junction here, or at the output of that transistor is probably better. Well, this is the, yeah, that's linked anyway, so I think we need to check an R42 what's going on there. Okay, the readings on the transistor, on the TR7, So that's the output, which is barely visible. That's one end, and if I can see the other side, that's the other side. So something is happening here. That's on the signal diode, and that's the R46. So that goes into the base. So something is happening, but the output doesn't reflect that. I want to see much closer to 0 volts, and that's 14 volts. So it's pulled up by the transformer. Alright, let's unsolder it off and have a look into this transistor. I need to figure out what it is, but I think it's a normal transistor. Well, that was close, but only quite. Can you see that? It's a 4.7 volt Zener diode, and it measures about 800 ohms in both directions. Come on. Difficult with one hand. So no matter which direction, it measures 880 ohms, so this is short. So it's actually this Zener diode, and it's a standard Zener diode, 4.7 volts. That is explaining why this is not down to a reasonable level, because it just pulls that one up, and the whole transformer current goes actually via this transistor down to the negative. Ah, by the way, the transistor test's good. It was suspect because of the signal shape, but obviously if that voltage is wrong, it's not going to work. As always, I got zillions of diodes, 3.6, 5.1 and some other ones, and these are 5.1 and 5.6 and 2.4 whatever, but I have no 4.7, so to get the thing going we use a 5.1 and see if it works. Okay, new diode is fitted, hopefully the right way around, I think so. Ah, look at that, that looks much different. That's more like it. Okay, switch the kettle on, and then increase the load. Look at that, we're driving current here. Come on, L1 1.8 amps. It should be about 3 amps now. Yeah, look at that, it's working. And it triggers nicely, that's exactly what I want to see here. And the kettle is boiling. Okay. Let's crank that up to a little bit more, so it should be around about 6 amp-ish. Yeah, 7.4, 7.1. Don't know if it's visible, there may be some glare here. So some, yeah, come on. Hard to see. 7 amps. I'm demanding about the right way. So kettle is boiling, thing is running. Let's go up a little bit further. That's input current, so the output current is different. So that's 8 amps now. And my kettle is boiling. Let's turn that down. 0, no output, or very little output actually. 200 milliamps, 300 milliamps. Yeah, there's still a bit of residual voltage, but it's pretty much nothing. 100 milliamps. Yeah, there is just a ramp generator in it. Now, because now it's off. Now, as soon as we drive current, you can see it's coming on. And now the demand is off and it's still glowing, so the down ramp, look at that, it takes some time to get down to 0. Now it's off. Yeah, there's a ramp timer in it. Okay. Unfortunately I can only measure the, so that's probably about 7 amps. 5.2, 5.8. Ah, sorry, some This always switches back to total current. My kettle is already boiling here, 7.8, and we're on full back here. So we're good. The amount is gone, and it's coming down slowly. I don't know how good it's visible because there's some glare. So if you look at that now, it's off now. Kettle is off. Demand is 0. Let's demand something. 2.9, so that's about 3.5 amps. That's 4 amps. But it does work. I can crank it up to 10. Hopefully it doesn't pop my fuse. That's about the maximum get out on the input current, and the kettle is boiling. Okay, yeah, looks about right. Yeah, that's about the maximum it will do. Okay, fine. Perfectly fine. Right, let's have some dinner and then we'll come back. Well, that transistor is quite an interesting one. Luckily it didn't fail. It does 80 volts and peak pulse current is 6 amps and this maximum power dissipation is 1 watt. That's quite a lot for such a small transistor here. Look at the size. I may not have a replacement for that. But anyway, it was just a simple Zener diode which just failed at some point. Anyway, let's power it on again and leave it running on low power for a little bit just to see. Now when you power it on, it comes up a little bit and then it comes down once the current regulator realizes there is no current or no current demand, because our demand is 0 here. It just cuts off. There's a lot of delay in the system just to make sure everything is stable and doesn't chuck around. Come on, 1 volt. That power supply is a bit twitchy when there is no load on it, because the input has not really any load. It's just funny. Okay, 1.4. We're driving some current, actually 2 amps on the mains. That doesn't mean we're driving the same on the output, because the output is rectified DC, and that's the reason why it's a kettle. You can't really use something else. Otherwise I would just use one of these fan heaters, but the motor doesn't run DC. So yeah, but it's okay. I'm absolutely happy with that. I just leave it running for a little bit to see if everything is stable. But you can see now it fires downwards, and that basically stops that triac. Where is it? If it fires downwards, that stops that triac from conducting. So well, it was a bit tricky to figure out what's going on in that circuit, because I have no proper circuit description, so I had to figure it out on my own, because there's lots of interacting with the current regulator. What it technically is, it's a controlled rectifier. Let's walk that open here. Just covering the name here. So it's a rectifier, basically 4 thyristors, a normal thyristor bridge, which is fired with these transformers here, and obviously you need to sync it with the mains that comes from here. You got a 2-way rectifier which gives you 100 Hertz into this circuit, which is the pulse former, and the firing point actually is determined by the current regulator. There's a current transducer somewhere down here. That's the current transducer, and so it matches the input demand with the current and holds it stable. That's all it does. Yeah, it's a pretty simple piece of kit. obviously purposely built for controlling dyno coils, and yeah, but that's what it is. The rest of the circuitry works okay. I checked the voltages, they're all good. Apparently the customer did it as well, because that's the drawings from the customer. So they checked all the voltages, but apparently when it went into the electronics they probably went lost. Okay, to put that up again, it's always resetting to the main screen here. Well, that's now almost 10 amps. I can't do any more. Now the kettle is boiling. I can't do any more because the resistance of the kettle is too high. The dyno coil has a lower resistance, and but it's fine. I'm drawing 10 amp mains current. That's pretty much what the output station can do. Yeah, happy with that. Not getting hot. We just leave it idling for a little bit with a little bit of demand, just to see if that doubt survives. But I think it does. And there's no particular. It was a normal quarter of a watt. See that? By the look of it, there is not much current going through. Well, that's what it is. So this is the negative side of the transformers, and this is where the positive side comes from. And these are the firing transformers, and that's the latching resistor transformer. And that's all on the other side, which is here, which is the high voltage corner, and that's the low voltage control side. Well, that's it. It's not rocket science. Basically, simple phase angle control with a few extras. There's not much more to say. Tell the customer it's working. I think he might be happy. He gave me another one, but that's a different style. That's for water break dyno, which has no high voltage control output, or which has no high voltage coil output. It's just low voltage stuff. So we couldn't use any parts of that. We didn't need to, because we had everything we needed. There's also a massive power supply inside. You can see that big transformer down there. That's actually for the low voltage supply of the rest of the system. It's all covered in that power module here. I don't need to show how to put it back together. Simple job, just put the screws back in. And another one fixed. So it's just doing a final test after assembling everything, just to make sure it works. And yeah, we have a current transducer on the output to see what's going on there. And we got the kettle back as a load resistor. Okay, so just verifying what we're getting here. So this is a little bit, and now we're going full wave. This is the max you can get, and you can hear the kettle is boiling. And now we reduce the power. And that's the residual, and then at a certain time it just pops off completely. It's off now. Okay, so kicks in, full load, nicely done, and no load. Okay, I'm pretty happy with it. So it does what it's supposed to do. It wasn't the easiest repair, but at some point you're going to find it. It's just a matter of time. Anyway, thanks for watching. Thanks for subscribing. Until next time.